Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, remove zero-sum consecutive nodes from linked list. So here we have a linked list, and what we want to do is repeatedly delete consecutive sequences that sum up to zero, where the values sum up to zero, until we can't anymore, okay? And then after that, we want to return the head of the linked list after that. So you can think of it as collapsing. When the sum is zero, you collapse all of them. So if we take a look at this linked list here, 1 plus 2 is 3, and then when you get minus 3, you collapse it, okay? And you may ask, well, should we collapse this one or should we collapse this one? And the answer is it doesn't matter, because any answer that does collapse until we can't anymore would be accepted. So in this use case, if you had collapsed these two and end up with 1, 2, 1, that would be accepted as well. So that makes it easier. This example, we could collapse this here, and we end up with, because this is 0, we end up with 1, 2, 4. If we do this one, we collapse these, and then we end up with 1, 2, minus 2, we collapse these, and we end up with 0. Or you could do collapse 5, because you get 5 and then minus 5, so you collapse those. So that's the idea. Now, how do we solve this? We'll do first the simplest possible solution, and then from there we can do a more sophisticated one. So the first, simplest first solution is to convert the linked list to an array, and then collapse the array until you can't anymore, and then convert it back to a linked list. So that's pretty straightforward. So let's just write it down, and then from there we can do a solution that doesn't convert to a list. So just first, converting a linked list to an array, you just define your array. Let me just refresh this so that we get highlighting. So first you just convert it to an array. So basically you just have this pointer to the linked list, and each time you advance it and add the value. Okay, so by the end of this, we'll have in A, we would have the same values here. And now we can just collapse it until we can't anymore. So we need to just define a function to collapse. And since if you look at the constraint here, we have up to 1000 nodes. So this should be a pretty simple two loops. So how do we do that? We create a new list, and then we go through each range. If any range is equal to 0, we just collapse. And by collapsing means if from I to j the sum is 0, we just remove that I and j. What does removing? Well, we can just return a list for anything before and anything after. So let's say you have I here, j here, and then you had something before. So and the sum here is 0. What do you do? Well, we just return this plus this. That would basically give us a list without the range that sums up to 0. Okay, so that's what we are doing here. Now, this collapsing, we want to keep doing it until we can't anymore. What does can't anymore? Can't anymore means we do a pass and we don't find any range that sum up to 0. Okay, so how do we do that? Well, first we need to initialize with a list. Let's call it collapsed. And then we can, while the collapsed is different than the current list, keep collapsing. Okay, so but we also need to say we shouldn't keep collapsing the same list. We need to collapse what we previously already did, right? So that's what we do here. And now we can just create, at the end of this, what we have here, we stop only if we can't anymore, okay? And so now when we can't anymore, we can just construct back our linked list. So we just need a dummy linked list to hold the beginning of just a node before the beginning, so that we can return at the end the next value. And then we go through this collapsed list and we add each value as a node. So in this case, for example, let's say for this one, we would have here collapsed would be equal to 3, 1. Okay, and so we'll just say 3 first, 0. And then point that 0 to 3, a node of 3, and then go to the next and point that to 1. And our dummy node would be pointing at this 0 here. Dummy node would be pointing here. And so to return, we want to return 3, 1. And so we return dummy.next, which would be here. Okay, so that should be straightforward solution. If we run this, submit, it should get accepted. Okay, it does work, but if we look at the term complexity here, O of n here, n is the length of the linked list. O of n here, because at most we will do, let's say, n times if each element is 0. So O of n plus O of n, and this is O of n as well. So O of n time, but the problem is we have this extra list that has length O of n. This extra list also each time, which has length O of n. So we have a lot of extra space we are using here. So how can we do this without too much extra space and without converting to a linked list? Let's see how we can do that. Sorry, without converting to an array. Let's see how we can do that. Okay, so let's see how we can tackle this. So if we take the first example here, the main idea is, let's say you are just using an array, not a linked list like I did here. How would you do this? Well, how would you do this in an efficient way? Well, one way to do it is to keep track of the sums you've seen so far, right? And so just a hash map for the sums and the position you've seen the sums in. And so, for example, here you can say even before, just to seed your map, this is usually good. You can say maybe we have a sum of 0, maybe at index, let's say, you could either do at index -1, or you could say, you could add 0 to the array and have this at index 0. It doesn't really matter. And then we have a sum of 1, a prefix sum of 1 at position 0, prefix sum of 3 at position 1, and then prefix sum of now of 0, right? Because here we have 3 minus 3 at position 2, prefix sum of 3 at position 3, prefix sum of 5 at position 4. Now, why is this useful? Well, look at this. Look at what we have here. This 0 and this 0. Okay? When we are at this prefix sum, we will find that we've seen this before. We've seen this value before. And so since we've seen this value before, that means you could actually just collapse all of this. Collapse all of this and end up with just position 3 and 4. Okay? So basically what this means is that if we find a prefix sum that is already in scene, then that means we can collapse. Let's say this prefix sum is at position j and what's in scene is at position I. That means we can collapse I to j. Okay? So that's the core idea here. Because if you have 0 and you had 0 before, prefix sum is just the sum, right? And if you, let's say, have 0 and now you have 0, that means what was here is a wash, which means it's equal to 0. Same thing, the value doesn't have to be 0. If you had 2, a prefix sum at position, let's say 2, at position maybe 4. And now you have 2 at position 8. What does this mean? That means the values in this range here didn't add anything, right? So that means the values here didn't add anything. So so it means their sum is 0, right? So that's the core idea that we'll implement. There is one thing we will do. So we will build this scene from just the linked list. We don't need to convert to an array to build it. We can just go through the linked list and build it. And then once we build it, what we can do is just go through our linked list again. So let's say our linked list here with this scene now is 1 to 2, 2 minus 3, to 3 to 1. So we'll go through it and we'll look at each value. We'll keep track of a prefix sum. So first it's equal to 0. And when we go here, now it's 1. Do we have any value 1 in scene? Not yet. Do we have any value 1 in scene? So at 0, we add this value, okay? And then do we have any value? No. At 1, no. And so we keep going, because if we use just this value, we'll just make that next equal to 2. So same thing, it doesn't change much. At 3, same thing, but our sum now is our sum now is 3. So here we are here, and then we look at what is the prefix sum of 3. Same thing, we are still going to minus 3, but then when we have minus 3, now we have 0. Did we see 0 before? Yes, we have 0 in the scene. So what do? Well, we need to point the current value, which is now here. We need to point the current dot next to be the position, the prefix sum, which in this case, it's not going to be a position, it's going to be a node. So here, instead of adding a position, if we are doing a linked list, we'll just point to a node. We can just point to the next dot node, because basically anything from current to that node at the prefix sum was a watch. So the sum was 0, so we need to get rid of it. So what this would mean is that we will point our current, which was, we will point our current to this one. Okay. So basically when we are at this 0, we'll find that we have this 0. So when our current is even before at the dummy node of 0, we have a 0 already, so let's just point to it. So this is a wash. Okay, so that's the idea here. Okay, so that's pretty much the idea, is we construct the prefix sum, and since we have a 0, we know that anything in between was a 0, so at the start, at dummy node 0, we'll just point this to this one, to the next of this one, which is this 3 here. Okay, so that's the core idea. Now let's take another example just to make sure this is clear. So let's take 1, 2, 3 minus, let's actually do it with a linked list just to make sure it's super clear. So 1, 2 to go to 3, go to minus 3, go to 4. Okay, so we will build first our scene. And now first we start as 0. Let's call it at the front, which in our front, let's have a dummy node here, just so that we don't lose the pointer to 1 here. And so it's going to be that, let's call it front. Our dummy node here, let's call it front. So that has a value of 0, and now value of 1 points to, let's call it node 1. Okay, let's actually do the entire thing. So the sum of 1 points to this node. Okay, minus 3. And now we go to the sum 3, that points to 2, 3 minus 3, and then 4. And then the node minus 3 points to the node. We do, this is 3, but then when we add this 3, it's going to be 6. Okay, 6 now points to 3 minus 3, 4. And then when we add minus 3 to 6, that's going to be, to minus 3, that's going to be 3. Okay, now 3 points to minus 3, 4. And then when we add 4, 7 points to 4. And that's what we have here. Okay, so now we do another pass to collapse what we've seen before. So first we have 0. Do we see 0 before? No. So we keep that 0. 1. Do we have 1 in scene? No. So we keep 1. Do we have 2? And then we have the prefix sum now is 3 because 1 plus 2. So do we have 3? Yes, we do have 3 here. And so we should point. So we should point our next to the next of the prefix sum, which is this node here, 4. Okay. So we point that to 4. And we end up like this. And now we removed what was a wash here. Okay, so that's sort of the idea. Create a scene. so that you can know what the same values that you have later on, so that when you find a value and you have the same before, you know the range in between is 0 and you can just point to the next one. Okay, so that's the core idea. Now let's build it up and make sure it passes. Okay, so let's do this. So the first thing we said we need to do is create our front, which is going to be just a dummy node that is 0 but has the next value as the head, right? Because we will just put 0 in front of the linked list, and we'll start our traversal from that front node. And then we'll keep track of a prefix sum so that we add it to scene, and then we need a scene hash map, right? And so first the prefix sum is 0, and our scene hash map needs to be need to have just the value 0 for this dummy node front, right? So this would be equal to 0, and then we have a scene that is equal to 0 that points to front. Okay, and now we'll just do while current equal to current.next, and we need to keep track of the prefix sum so far, so current.val. And the scene for prefix sum is going to be equal to, what should it be equal to? It should be equal to the current node, right? We are saying we have a prefix sum of, let's say, 3 at this node, and so we say current here. And now that we build our prefix sum, we'll do another traversal. So we need to initialize again to front and keep going. We'll do the same traversal. But what should we do in this traversal? Well, we should, again, we want to keep track of the prefix sum. So when we are at, let's say, value of 2, we want to know if in the future we have that value of 2, which means the range in between is 0. And so we will keep updating the prefix sum. Now, for the scene of the prefix sum, .next, what do we want to do with this? We want to point to the current next. Okay, now you may say, okay, what if we don't have any values in the future that is equal to this prefix sum? Well, in that case, we'll have only the current value, so we'll point just to the next node of the current node, which is equivalent to not doing anything. So we don't need to do a special case for if there is no same sum in the future. But if there is a same sum in the future, we'll just skip to that sum because anything in between is equal to 0. Okay, that's the core idea. Now, once we do this, we can just return our head of the linked list, which, because front is a dummy node, is just front.next. This would be the collapsed linked list because we collapse using this here. Okay, and now if you look at this solution, O event traversal, another O event traversal here, so O event time overall. In terms of space, we are only using this extra scene map, which is oven. So it's still oven time, oven space, but it's better overall since we are not converting it to an array and we are not creating an array each time. A new array each time will collapse. So if we run this, submit, it does get accepted. Okay, and yeah, that's pretty much it for this problem. Thanks for watching and see you on the next one. Bye.